Right, let's begin. Sound lesson 4, isn't it? Last lesson, just to recall, we looked about the ear and how sound travels through the ear. So, are you still sure you can name all the parts of the ear and what can happen to the ear if, for example, we damage the hairs in the cochlea, we have a perforated eardrum, we get too much wax, etc. Do you remember we talked about the auditory range? And we use the term ultrasound to explain something that's too high a frequency to hear, and infrasound to explain something that's too low. Hopefully you can recall those terms because they're going to be important today. In today's lesson, here are our objectives. Let's have a look. We're going to describe some uses of ultrasound. So last lesson we said ultrasound was something above 20,000 hertz, too high for us to hear, but let's have a look at some uses of it. And then we're going to explain how sonar and echolocation work. It's not going to be a massively long video today. Both of these things are fairly straightforward to explain. So let's just do it. Before we get into that, I just want to explain how sound can interact with objects. And light would be the same as well. When sound approaches an object, three things are possible. The first thing that's possible is it might be reflected off an object, and we'd recognize that as an echo. Yeah, you go into a cave, you shout, the sound reflects back, you hear it, that's your echo. The second thing that we might be familiar with in our everyday life is a sound might just pass straight through it. So you could be sat in your living room, a big car or a truck or a bus or whatever drives outside. The sound from that can travel through your solid glass or even the walls of your house, and you can suddenly hear it. It's been transmitted through that material. But one thing that we don't often look at is this one here, absorbed. A material can actually absorb a wave, take the energy of that wave as that wave is traveling through it. It's easier to imagine that with light. Now, we know that if we leave something out in the sun, especially if it's painted dark or black or something like that, we can pick it up and it's going to feel warm. And that's because it's absorbing the energy from the wave. The light isn't traveling through it and not all of it's reflecting off it. Some of that energy is being absorbed. Sound does the same thing, and this makes sound pretty useful for medical purposes, especially ultrasound, which has such a high frequency, a high energy. Here we can see somebody using ultrasound to work on the some scar tissue in somebody's wrist, and the sound from the ultrasound machine, that high energy machine, is being absorbed by that scar tissue. It's absorbing that energy and that softens that scar tissue up. We can also use ultrasound to break up kidney stones in the same way. They will absorb that energy or some of that energy from that ultrasound and break up into small pieces, making them easier to pass out. So yes, so ultrasound for medical purposes, they are two fantastic examples, and they both rely on, like we said here, the energy from the ultrasound being absorbed as it passes through something. Now, why ultrasound? Why not normal sound? Well, I guess there's a couple of reasons. The first one is if we use a normal sound, it's going to drive everyone absolutely potty because a sound would have to be incredibly loud. It needs a lot of intensity and energy. So it would drive everybody nuts just to be sat there being able to hear the sound. But also ultrasound has a very high frequency, and frequency is linked to energy. So just by the very nature of it having that high frequency, it's going to have more energy that can be absorbed when we pass it into kidney stones or scar tissue, etc. Now, we're not really bothered about sound being transmitted or passing through objects, not for today's lesson, or really anywhere in the topic. But we are interested in sound being reflected. That will give us our second learning objective, which is echolocation. And I will touch on ultrasound for babies as well. Now, have a look at this boy, and I will put a link in the class charts when I put this video out for you tomorrow of somebody who can do what this boy can do. And if you can see on the screen there, this boy is blind, but he can use clicks. He makes clicking sounds with his mouth, and by listening for the echoes where they come back, he can kind of like form a picture of his surroundings. A bit like Daredevil if you watch the your superhero stuff, but not the Netflix one because that's too old for you. You're year 7. So anyway, this is a skill that humans can learn. We don't tend to learn it or pick it up because we can see, and we don't need to pick this up. But if you're blind and you're young enough, it is definitely a skill you can learn. And it's called echolocation, basically sending a noise out, waiting for that echo to come back, and then using that to form a picture of your surroundings, a bit like radar. This wouldn't necessarily be ultrasound if it was the boy doing it, because if the boy's doing it and he's clicking or making noises with his mouth, well, he could hear those noises, so they have to be below that 20,000 hertz. So he might not be using ultrasound, but the echolocation is the same. Now, oh, come on. There we go. Let's have a look at examples of it in nature. And you've often heard the phrase, I'm sure, blind as a bat. Bats have very poor eyesight, yet they come out at night when it's darkest. And despite the fact that it's dark and they've got bad eyesight, they don't fly into walls, they don't fly into trees, and they're capable of catching their prey. And the reason they can do that is because of the same echolocation, using sound as like a radar system. They are constantly screaming and screaming and screeching, but they are doing it at ultrasound frequencies, so we cannot hear it. But they can pick up their echoes, and using those echoes, where they come back, the direction they're coming back in from, how loudly they're coming back in certain directions, they're able to build up an image of what's around them, and even hunt down tiny things like moths using that ultrasound. So this is again, echolocation. Echo, because an echo is reflected sound. Location, because they are locating things using echoes. A form of echolocation, although we don't really call it echolocation, but it's kind of using the same idea. My computer seems to be a bit slow. There we go. Is sonar. So what is sonar? Well, sonar is essentially what ships use when they go over the ocean, and they can use it to build up a picture of what's underneath the ocean. And it's similar technology to, or a similar idea to, what we would use in an ultrasound scan when we're scanning for babies. We'll talk about those in a second. Now, this ship here, ignore the writing here. I'm not going to talk about the fish. Detecting the fish is echolocation. We've done that. But I'm going to change this ever so slightly. This ship is going to try and map out the floor of the ocean. What it's going to do as it sails across the ocean is it's going to build up a picture of how deep every little bit of that ocean is. And then it can use that to build up a map of what the ocean floor actually looks like. So how does it do that? Well, to figure out how deep the ocean is, it's going to use ultrasound, and it's going to have a speaker attached to the bottom of the boat, and that speaker is going to make an incredibly loud noise. And this is possibly why they use ultrasound, because if it's a very loud noise, which it would have to be to travel down to the bottom of the ocean and back, you're probably going to deafen your crew members if you're not using ultrasound. There may be other reasons. But it makes a very loud noise that we can't hear in the ultrasound range. That noise travels down where my mouse is traveling. It hits the ocean floor and it bounces back up again. And it picks up the echo. Now, it shouldn't take too much understanding to realise that the longer it takes to hear the echo, the further the sound has had to travel. Yeah, the deeper the ocean is, the longer it takes before we can hear the echo. That's common sense. If we hear the echo very quickly, then the ocean is shallow. Yeah, the sound's not travelled far in that area. But how do I actually use maths to figure out exactly how deep the ocean is? Well, we're going to use an equation that you'll have done at primary school. You'll have done it when we did forces earlier in the year. Very simple equation that is distance travelled equals speed times time. You may have learnt it as speed equals distance over time. All right, it's just a rearrangement of that. The distance something travels is the speed it travels at times the time taken. So what information will you be given in the question? You will be given the speed that sound travels in the water, and it will travel at different speeds in salt water to fresh water. Or if this is an ultrasound question, remember it uses the same idea to build up a picture of a baby. It will tell you the average sound that the average speed that the sound travels through as it goes through the woman's belly and the womb, etc., to bounce off the baby. So you'll be given the speed. The time, you might have to figure that out from a graph that the question gives you, or it might just tell you. But the time is going to be how long it takes for the sound to leave the boat, bounce off the ocean floor, and come back again. Or to leave the handheld thing, bounce off the baby, and come back again. All right? But we can't just simply slap those two numbers into distance equals speed times time to get the depth of the ocean. If we did that, we would get the distance the sound had travelled. Okay? But let's think about what we're trying to figure out. We're trying to figure out how deep the ocean is. That is different to the distance the sound has travelled. Let me show you why. The distance the sound has travelled is this. It leaves the boat, hits the floor, bounces back to the boat. So the sound is travelling twice as far as the ocean is deep. So to use the equation to calculate how deep something is, or how something far away is using ultrasound, we are going to use the equation distance equals speed times time divided by 2. All right, we're going to half the answer. Now, with ultrasound for a baby, it will be the same thing. The C wouldn't be the C, it would be the mother's belly and the womb. The ocean floor would be the bones of the baby, and the boat would be the thing that they put over the woman's belly to emit the ultrasound. So hopefully, you might want to listen to that bit once or twice just to pick up why we've got to half the distance in that equation. Think about the equation, but hopefully you've got an idea now of a couple of uses of ultrasound, why they can be used, and you can apply this equation. Now, one question you might get is, somebody might say ultrasound doesn't give as clear a picture as we could get using x-rays, for example, certainly of the baby's bones anyway. So why do we use ultrasound instead of x-rays? Essentially, x-ray radiation is just that, it's radiation. It's harmful, and although once we're grown up, it's perfectly safe to have 1 or 2 x-rays. You don't want to be going in and having loads and loads of them, but it's perfectly safe to have an x-ray when you're an adult. But when you're a child and you're developing and you're not very big and your cells are constantly dividing, there's a chance that the x-ray could damage the cells and cause the baby harm. There's no chance of that with ultrasound because it's not radiation, it's just sound. And I think that is pretty much it. There'll be some worksheets, obviously. Other than that, I will be back with Monday's lesson. Bye-bye.